All right, so I'm going to talk a little bit about aromaticity, and then first to kind of talk about aromaticity, I'm going to talk about benzene. So aromatic comes from the name, the aromas. A lot of these molecules have aromas. They call them aromatic compounds. And this is really kind of a big puzzle for chemists for a long time. But they came up with this, finally, this, they call it Kekule structure, where the benzene ring, you can see the resonance forms here, where the pi bonds are rotating, or sometimes people even draw it as a circle. It's 6 electrons in a benzene ring in pi bonds delocalized by resonance, right? So this is, we call this conjugated. We call this a conjugated system, which is just a fancy way of saying, you know, when pi bonds are lined up next to each other, we consider this to be conjugated. A benzene or aromatic compounds are in a ring. That's a special level of stabilization. Pi bonds want to be conjugated. That makes things stable, right? They do resonance, a stabilizing factor. So benzene is an example, a special example of that. So just quickly, just some common names. We've seen these in lab, but we want to make sure you've seen these before. So benzene with a single substituent doesn't need a numbering, so there's common names. You could say toluene is the benzene ring with the methyl. Phenol is a benzene ring with the oxygen. Aniline, benzene ring with the nitrogen. Benzoic acid, it's called anisole of the ether. Benzene sulfonic acid, acetophenone, benzophenone, benzaldehyde, styrene, ethylbenzene, nitrobenzene, fluorobenzene. A lot of common names, but I just want you to see these kind of things. The other way we talk about disubstitute benzenes, we use something called Orthometapera. So if I have a benzene ring and you have 2 things on it, to describe the relationship from X, there's something called ortho position, a meta position, and a para position. And there's a meta and then ortho on the other side too. So this helps us to tell us what the relationship is between 2 different substituents on a ring. So these 2 are ortho, dichloro, meta, para, ortho, meta, para. So this helps us decide where they're at a little bit. I'm not going to ask naming questions, but I want you to have seen this and know what it means when you see ortho, meta, and para. It's only used to do disubstituted rings because you're really only talking about the relationship between 2 things. So when you start to have 3 things, you're going to have to use some numbers instead. Di, ti, tetra. But again, just want you to see it. Not going to ask a lot of questions on this, or any questions on this. Okay, so let's come back to that, talking about benzene and why it's special. Then we talk about being a conjugated system. So all these p orbitals lined up, right? So these p orbitals all lined up. We have electrons in pi bonds. They flow between these 6 p orbitals, right? They're kind of flowing this way. And I just kind of think of it, right? Again, like this, or sometimes people will draw it kind of circle electrons there. So due to resonance, these bonds are a little different. They're not quite single bonds because of resonance, so they're a little bit shorter than that. And there's also a really big stabilizing factor as well. So that stabilizing factor is shown here. You can really see the difference here. So it takes a lot of energy to essentially, what this graph is showing you. If I want to go to a cyclohexane, get rid of all the pi bonds, right? How much energy is it going to take? It's going to take a lot of energy to get a benzene ring to be reduced. And that's just telling you there's something special about a benzene ring. So to turn all these alkenes in a benzene ring, it's different. It's more stabilizing than, say, 3 pi bonds not in a ring. So there's something special about being in a ring. Okay, so benzene, aromaticity, that's a classic example of aromaticity, something very stable. So something special about having not just conjugation, right? We know that's stabilizing, but conjugation in a ring. There's something special about that. And that's called aromaticity. So a benzene ring is an example of aromaticity. How do you know if something's aromatic? How do you know if it has a special stability? Well, here are the rules. They're called Huckel's rules. So it must be planar, which means it must be flat. It must be in a ring. The ring must be completely conjugated. And it must have 4n plus 2 pi electrons in the conjugated p orbital cloud, where n is the integer. So now that seems complicated, but let's just remember, if you can always remember benzene's aromatic, you can come back to this. You see all these are sp2 hybridized, so it's planar. It's in a ring, and it's fully conjugated, right? There's all the p orbitals are lined up. There's no sp3 atoms at all. That's kind of what this is asking. Are there any sp3 atoms involved? And what it's saying here is you must have 4n plus 2. So what that means is, if you had 4n plus 2, a little bit of math. So 4n plus 2 equals the number of electrons in the system. So how many electrons are in this system? Well, there's 2, 4, 6. So if we set this equal to 6, a little bit of algebra here, and then n is a whole integer. That means this is aromatic. That's one way to look at this. Another way to look at this, instead of worrying about, this whole shebang, is there an odd number of pairs of electrons? So odd numbers of pairs. So in this case, 1, 2, 3. That's odd. So this is aromatic. Why is it aromatic? Because it's planar, it's cyclic, it's completely conjugated, and has an odd number of pairs of electrons in the ring. So let's look at some other examples. So there is something called antiaromaticity, which is essentially all the other rules apply except the number of electrons. So instead of having odd number of electron pairs in the ring, we have an even number of electron pairs in the system. These are really unstable, so just as aromatic compounds are very stable, these are really unstable. So you can see conjugated, no sp3 atoms, it's all in a ring, but it has 1, 2, an even pair. So this is anti-aromatic. These are pretty unstable. Again, here, in a ring, all conjugated. This is choosing to be sp2, right? So this lone pair can be in a p orbital, so we can do resonance, but it's going to be really unstable because it's in a ring and has an even number of pair of electrons. Bigger molecules like these actually will not be planar, won't be flat, because they'll kind of torque themselves to not be flat, to be more stable, because they want to get things away from each other. A lot of times molecules don't like to be flat. So obviously there's aromaticity, which is really stable, and there's anti-aromaticity, which is really unstable, which doesn't happen very often. Most things, though, are non-aromatic, right? So molecules that don't obey Huckel's rules in one or more way, right? They're not flat, they're not in a ring, or they're not have a certain number of electrons in the system. So most compounds are not aromatic. So classic example is cyclooctatriene. Now if you looked at this, you'd say, if I just looked at it flat, I'd say, well, this isn't a ring. They're all sp2 hybridized, so it should be planar. But I have 1, 2, 3, 4. That's an even number. Even means anti-aromatic. So what this molecule actually does, it puckers like a cups. So when it does that, notice how these p orbitals are still lined up, but now these two right here are no longer lined up. So it puckers itself to avoid being anti-aromatic. Why is this molecule non-aromatic? So it's a non-aromatic molecule. Why is this non-aromatic? Well, it's non-aromatic because there's an sp3. It's not conjugated. It has an sp3 atom there, so it can't be aromatic. Same with this one. Again, conjugation, great, but you have to have the whole system be in conjugation in a ring, right? Everything needs to be sp2 or sp hybridized. So this is non-aromatic as well. Okay, so we've seen a couple examples. I showed you one with the negative charge, but what would happen if we had anions or cations? How does that play a role in this? Well, same as before. So this is actually something they just did in an advanced organic lab. So this CH bond is actually pretty acidic. Now why is it acidic? Well, because if you put a negative charge there, the base here would have resonance, but not just resonance, it's actually going to be aromatic. We talked about resonance is good, aromaticity is even better. So you look here, right? It's sp3 here, but then it becomes sp2 to form that uninterrupted pi system. Now look, it's all flat, it's in a ring, and it has 1, 2, 3 pairs of electrons. This is an aromatic species, so that's going to be really, really stable. So an anion, right? Negative charges can be part of the p orbital system, and that also will be aromatic. Also, you could have, right? So let me show, right? This is what I'm talking about, the acid-base chemistry. That gets us to this, which is aromatic. We could also have a leaving group just leave, right? So something that was sp3 hybridized now becomes sp2, and so they're showing it in such a way if I put a plus charge there, what happens? Now, I have a ring. Carbocations are sp2 hybridized. So it's all conjugated. There's all lineup of p orbitals, right? So it was sp3, lost the chlorine, now it has an empty orbital. And I have 1, 2, 3, an odd number. It's okay that there's an empty orbital there. I have an odd number. It's in a ring. It's all conjugated. It's aromatic. So this is actually a really reactive, good leaving group. So an anion way to have aromaticity and a cation way to have aromaticity. So always the rules still apply. Planar, in a ring, conjugated, right? No breaks, no sp3 atoms, and an odd number of pairs of electrons. So we've talked about some of these heterocycles. Heterocycles is just a way of talking about rings that have things with lone pairs, so like nitrogen, oxygen, sulfurs. They're called heterocycles because they're heteroatoms. So again, we've seen some of these before, and this is just taking on what we've talked about, the reactivity here. This nitrogen is going to choose to be sp2 hybridized because now I can put its lone pair into a p orbital, which will allow it to do resonance. But in this case, it's even better than that because it's in a ring. It's all conjugated. It has 1, 2, 3 pairs. This is aromatic. Same with this furan. Oxygen is choosing to be sp2. One of the lone pairs will be in a p orbital, which can do resonance then, and it's in a ring. So how many pairs of electrons does it have in the resonance in the delocalized section? 1, 2, 3. Aromatic. Thiophene the same way. Pyridine. Everything's flat. Conjugated, no sp3s. 1, 2, 3 pairs of electrons in the p orbital system. This is aromatic. Notice this lone pair is not part of the pi cloud or the p orbital system. It's in an sp2 orbital. We talked a little bit about that when we talked about reactivity and hybridization states. So again, this nice picture of a pyrrole here and a furan just kind of show this. I think it's really important. Notice the nitrogen, sp2 hybridized, is choosing to be sp2 hybridized, has a p orbital, which you can put a lone pair in, which then it can share with all these other p orbitals, and that forms that p orbital system. But because it's in a ring, because it's uninterrupted, and it has 1, 2, 3 pairs, it's aromatic. Same with the furan. One lone pair is in an sp2 hybridized orbital. The other one is in a p orbital in the pi system, in a ring, uninterrupted. How many pairs of electrons? 1, 2, 3. That makes it aromatic. Odd number of pair of electrons. Final thing, these can kind of get fun. Bigger rings, these are fused rings. They're called benzenoids. These are also often aromatic as well. So you can take a look at something like naphthalene. It's a ring system, uninterrupted. All is a p orbital system. How many pairs of electrons are in it? 1, 2, 3, 4, 5. So this is aromatic. Phenanthrene, 1, 2, 3, 4, 5, 6, 7. Aromatic. All flat, all in a ring, aromatic. And you can go on and on and on. Lots of different types. Lots of practice for this. The biggest rules for aromaticity: flat, conjugated pi bonds in a ring, and an odd number of pair of electrons.